Hi there, Mr. Sutton here, bringing you the BC Calculus 7.5 Extra Practice Number 2 solutions on alternating series error bound. For this problem, let's say we have this series here that's approximated by this partial sum. So notice that the series and the partial sum are pretty much the same, except in the partial sum, we're only going to k, which is some constant, instead of infinity. So we want to find the least value of k for which the alternating series error bound guarantees that, well, this is a little bit crazy, s minus s sub k absolute values less than or equal to 0.0005. So we're trying to guarantee a maximum error of 0.0005 basically. So because we have terms that are alternating, and also if we recognize this larger, faster growing denominator, we're decreasing an absolute value to 0. Because we have this situation, that means that the error of using this polynomial here, which we can classify as this s minus s sub k, basically the difference between the whole series and the polynomial that we truncated this at, this error is going to be less than the absolute value of the next term. This is the alternating series error bound. So what is the next term? The next term, if we have a partial sum of this stuff that goes up to k, the next term is basically going to be this expression here, this summand, with k plus 1 plugged in for n. So this is going to be 1 over k plus 1 in a parentheses times 2 to the k plus 1. This is our next term if we already have the first k terms guaranteed by this polynomial here, this partial sum. So we wanted this next term to be basically no greater than 0.0005. So let's figure out where this equals 0.0005 on a graphing calculator. So to do this on the grapher, I've entered in the left side of my equation with an x instead of a k in my y1, and this constant 0.0005 is my y2. I just want to see where these intersect. Now for my window on this, because this is definitely going over things with a fine-tooth comb, we notice that my answer choices are between 6 and 9. So if I'm anticipating an intersection somewhere in that range, let me go to window, and let me just make my window, we'll go from 5 to 10. Just to give ourselves a little bit of slack there. So let me do zoom 0, zoom fit. And here is the left side of the equation. And coming right up, here is the right side of the equation. So we do have a point of intersection somewhere between 6 and 9 for sure. To see what it is, let's do second trace, option 5, intersect. And just press enter, enter, enter. And we come up with about 6.971 and some change. So there's my graph. We had a k value of roughly 6.9710. Now, the question is, are we rounding up or down? Because we have answer choices of 6 and 7. Well, the bigger my k value is, the more accurate my partial sum is going to be, and the smaller my error is going to be. So if I want to guarantee that my error is at most 0.0005, 6 isn't going to get me there. To get less than this, I've got to go all the way up to 7, which isn't that far from this term anyway. But we are going to have to round up to k greater than or equal to 7. So 7 is the smallest term then out of all these answer choices. So then we pick choice B. On this one, we have a Taylor series for sine of x about x equals 0 given by this series here. And we're told this converges to sine for all x. If the 9th degree Taylor polynomial for sine of x about x equals 0 is used to approximate sine of 2, so we're approximating sine of 2, we want to know the error in doing that using a 9th degree Taylor polynomial based on the alternating series error bound. Well, we look here and we see that we do have an alternating series, and for x equals 2, or really for any constant, these terms are going to decrease in absolute value to 0. This factorial term down here really drags things down to 0. So therefore, the error is going to be less than the absolute value of the next term. So now what is the next term? Well, we need to figure out what the current term is. We don't even know what n is to start with. If we did, we could just add 1 to that number and plug it in for n here. So they said a 9th degree Taylor polynomial. This is the key to figuring out where we are. Taking a look at this formula, the degree is basically the exponent on the x. You're not going to get to the 9th degree until you have an n value of 5, because 2 times 5 minus 1, that would give you the 9th power here. So 9th degree happens when n is 5. That means the next term, we're going to have an n value of 6, 5 plus 1. Now there's a little bit more that we have to also put in this absolute value for this next term, because we need an actual x value in there. But the x value is just going to be whatever you were plugging into the sine function itself, which in this case is 2. So given all that, we can write that error is going to be less than the absolute value of this term here, this formula, with 2 plugged in for x and 6 plugged in for n. So we're going to have 2 to the 2 times 6 minus 1 over 2 times 6 minus 1 factorial. And just simplifying this to get an answer choice, this is going to be 2 to the 11th power over 11 factorial. So that's going to end up being answer choice C. For this one, for absolute value of x less than 1, we're told that ln of 1 plus x equals this series. So based on the alternating series error bound, we want to know the least value of m such that the partial sum, the error using a partial sum from 1 to m of approximating this ln of 1 plus 1 is less than 1/5000th. So the key on this one is understanding that with your alternating series error bound, your error is going to be less than the absolute value of the next term. Now they're saying use the alternating series error bound here. So we're guaranteed that we have a series whose terms are alternating and decreasing in absolute value to 0. We just have to apply the alternating series error bound. Okay, well, what is the next term going to be if this is your partial sum right here? Well, if you've used up the first m terms, the next term is just going to be your formula here with m plus 1 plugged in for n. Now, since we're taking an absolute value for this, we don't have to write this -1 to the n plus 1 stuff. We do need something about this n down here, though. So I'm going to write this as 1 over m plus 1. And over here, I'm going to have 1 over 10 to the m plus 1. And so this is our next term, again, using the first m terms in our partial sum. And we want this is the error essentially. We want this to have a value of less than 1 over 5,000. Okay, so this is kind of tricky if you're just setting these things equal and trying to solve for m. Fortunately, we've got some answer choices of what m could be. So the fastest way to do it at this point is just to start plugging in these answer choices until we get a value that's hopefully less than 1 over 5,000. So let's try the answer choice 2. So we've got 1 over 2 plus 1 and 1 over 10 to the 2 plus 1. So what does that come out to? Well, this is 1 over 3. This is 1 over 1,000. So this is 1 over 3,000. 1 over 3,000, the denominator is smaller than 1 over 5,000. So this fraction is bigger than 1 over 5,000. We don't want bigger. We want smaller. We want something that is at least, or is at least no bigger than 1 over 5,000. So let's try choice B with m equals 3. So we've got 1 over 3 plus 1, which is 1/4. 1 over 10 to the 3 plus 1 is 1 over 10,000. So this is a 1 over 40,000 then, which is a much larger denominator than 5,000. So absolutely, this is going to be smaller than 1/5000th, which means that the smallest m value that guarantees this error bound is going to be m equals 3. So we pick choice B. For this problem, we have a Maclaurin series given for a function f by this series right here. Looks an awful lot like the sine function to me. But anyway, we're told that g is defined as g of x equals f of x squared. Our first task is to find the first 4 non-zero terms and general term of the Maclaurin series for g. Well, we've already got the Maclaurin series for f. To get the Maclaurin series for g, we just have to basically replace x with x squared in the f series here. So that's going to be, instead of x, we're going to have x squared in the beginning. And then this is going to be x squared cubed, which is going to be x to the 6th over 3 factorial. And none of the signs are going to change here. So we have minus there. This will now be plus x to the 10th over 5 factorial, minus x to the 14th over 7 factorial. And that's the first 4 non-zero terms. The general term, we're just going to have negative 1 to the n, x to the, let's see here, got to plug in, we're going to have x squared raised to the 2n plus 1. So this is going to be x to the 4n plus 2 then, all over 2n plus 1 factorial. And there's our terms. On this part of the problem, I want to find the limit as x approaches 0 of all of this craziness. So let's get a sense of what we're actually doing first. From part A, we saw that the g function was this stuff here, x squared minus x to the 6th over 3 factorial, and all the rest of it. We already did part A. So now we're just doing x squared minus x to the 6th over 6 minus, well, all of that stuff, all over x to the 10th. And this is just one big limit now as x approaches 0. Let's combine some like terms before we try plugging anything in. So we have an x squared minus the x squared in here, that's going to cancel. This negative x to the 6 over 6 minus minus plus x to the 6 over 6, that also cancels. So we're left with all the other terms in here from x to the 10th over 5 factorial and thereafter. But because we're subtracting all of this stuff, all of those terms are going to have reversed signs. So we're going to have minus x to the 10th over 5 factorial plus x to the 14th over 7 factorial. And that goes on forever. Now, to make this a little bit easier, I mean, you might notice if you tried plugging in 0 right now, you would zero out everything in the numerator and also the denominator, and 0 over 0 is never a good final answer. So what we can do to fix this situation in the numerator, it looks like we can actually factor out x to the 10th. Everything has at least x to the 10th here. That would leave us with negative 1 over 5 factorial. And then we'd also have, this next one would be x to the 4th over 7 factorial. And all the other terms after this would also have x's in those little mini numerators. So now these x to the 10ths can cancel out. So we really just have the limit as x approaches 0 of negative 1 over 5 factorial plus all the rest of that. At this point, if you plug 0 in, all of these terms that have x's in them are going to be zeros. So you're just going to be left with negative 1 over 5 factorial for that limit. And if you really wanted to, 5 factorial is 120, 5 times 24. So you could write this as negative 1 over 120. Either of those would be acceptable. For this part, we're letting h be the function represented as the integral from 0 to x of the g function, which from part A again, here's the g function. So we want to write the first 4 non-zero terms in general term of a Maclaurin series for h, and then we'll use the first 2 terms of that to approximate h of 1. Okay, so basically taking the antiderivative of all of this stuff. Now, the way that this shakes out with the integral from 0 to x is you're taking the antiderivative of everything here. It's all going to have t's. You're going to plug x's into those. You're going to plug zeros into those, and then you're going to subtract. All the stuff with, but all these terms, since they're all going to have variables, when you plug in 0 and subtract all that, you're basically just going to be subtracting a whole bunch of nothing. So really, when you take the integral of all this stuff from 0 to x, you just end up with the antiderivative of all this stuff with x plugged in, and you don't even need a plus c, because it's a definite integral. So going from left to right then, we're going to have, let's see, this bumps up to a 3 using our reverse power rule. So this is 1/3 x cubed. On this next one, we'll have an x to the 7th, and we'll have a 7 times 3 factorial down below there. This next one, we're going to have plus x to the 11th over 11 times 5 factorial. Then we have x to the 15th over 15 times 7 factorial, and we're subtracting that. More generally, we're going to have negative 1 to the n x to the 4n plus 3 all over 4n plus 3 times 2n plus 1 factorial. So there's the first piece of this question that we needed to answer. Now they wanted us to use our first 2 terms of this, so just these first 2 terms, to approximate h of 1. So if you want to be really cheap about this, you can write h of 1 is approximately equal to 1/3 1 cubed minus 1 to the 7th over 7 times 3 factorial. And since this is all constants here, you're actually done. You do not really need to simplify this. But if you wanted to, we have 1/3 minus, this is going to be 1 over 7 times 6 is 42. Well, 1/3 minus 1 over 42, 1/3 is really 14 42s. So this comes out to 13 over 42 when all is said and done. For the last part of this problem, they want us to explain why the approximation found in part C differs from the actual value of h of 1 by less than 1 over 1,000. So here is the h function, again, from part C. And remember that in part C, we approximated h of 1 by plugging 1 into just the first two terms here. So they want us to explain why that approximation basically has an error that's less than 1 over 1,000. Okay, so to do this, first we have to recognize that we have a series that is alternating, which is good. And also, if you plug in 1 for x, which is really what we're doing here, approximating h of 1, you'll notice that these terms are decreasing in absolute value to 0. Your numerator stays the same because it's just 1 to a bunch of different powers. Your denominator keeps growing. So since the terms of h of 1 are alternating and decreasing in absolute value to 0, this tells us by the alternating series error bound that the error, which is what they're talking about here, this difference between the actual value of h of 1 and the approximation, that error is going to be less than the absolute value of the next term. So our error then is going to be less than the absolute value of, well, what is the next term? If you approximated h of 1 using the first two terms, then the next term here is this x to the 11th over 11 times 5 factorial with 1 plugged in. So we're just going to say error is less than 1 to the 11th over 11 times 5 factorial. And we now need to show that this is less than 1 over 1,000. We could just write less than 1 over 1,000 and hope they take our word for it, but let's see what this actually comes out to. 1 to the 11th is obviously 1. How about 11 times 5 factorial? Well, 5 factorial is 120. So let's see here. If we have 11 times 100, let's just split it up here. 11 times 100, that's going to be 1,100. 11 times 20 is 220. 1,100 plus 220 is going to be 1,320. So this is really 1 over 1,320. And since that has a larger denominator than 1 over 1,000, overall it is a smaller fraction than 1 over 1,000. So we've shown then that this is less than 1 over 1,000.